Good morning. So this is our second period of today's class, and we are now going to continue with our ride dynamics last part, looking at the suspension design. And I am certain that you would understand well and appreciate the vehicle parameter influence on your suspension design. Hence, what is that its role in vehicle dynamic aspect. Though we are emphasizing more that moment, vertical dynamics, you see that the suspension do take care of other aspects of design of your vehicle, as well as your road holding, handling characteristic of the vehicle. So that's what I'm just going to highlight in this particular period in our lecture number L16. So lecture number 16, you're going to look at ride and comfort and active, semi-active suspension system. And you have got a thorough background for this to understand, as you know now deterministic models of vibration model of your vehicle, and how do you go about understanding the vehicle nature and its amplitude ratios and so on. And you also know now thoroughly the background of enforcement of standards that are going to give a pressure on OEMs to work on the vehicle design so that you get a good ride of your vehicle. And we also have characterized importantly the road profile through its power spectral density function, and we looked at its application through a simplest case of single degree freedom model. So if your degrees of freedom model is more complex and complex, you would seek the help of software like MATLAB tool, and you will be always able to incorporate your real road data given by power spectral density function, and work on finding out an RMS acceleration of your vehicle at different target locations. So with that, now let's have a specific small topic of suspension, which are called an active or semi-active suspension. There are many aspects to discuss. I'm just going to quickly take you through, but I leave it to you to do as a self-study, reading the textbook again, right? So let's go ahead. So when we say the suspension system, its overall performance is basically quantified by three aspects. One is vibration isolation that can provide. Another one is suspension travel. A third one is road holding. So when I say vibration isolation is what is very much relevant to what we are discussing now, called ride quality, ride dynamics aspects. So it has to isolate the energy that enters the vehicle from road surface irregularities to the vehicle. So that is what is achieved by vibration isolation. So good measure is what is Z1 by Z0. So the transfer function transmissibility ratio is what is going to dictate or going to decide on what is vibration isolation. And what is suspension travel? Suspension travel is relative displacement between your sprung mass and unspun mass. So the maximum relative displacement for the given, so Z2 minus Z1 by the maximum relative displacement of that for a given road input is what is the second measure called that's going to be called as a rattle space. Rattle space. So rattle space is that there are bound and rebound stops. Between that, you should have quite sufficient space so that you can accommodate all the suspension components and electronic gadgets nicely, and they are always be, their placements are reliable and they are functional. So for that purpose, you require this suspension travel space, rattle space objective. So I require to have this values to be minimum. So this ratios to be minimum to have it have good space available. So if that is more, that means there is more travel. That means there can be a hit by the stoppers, and that is not preferred in the vehicle. So wheel hop will go and hit unsprung may hit your rebound or bump stops. So that is not preferred. So that's what is to be minimized. So these all three quantities are to be minimized. So here it is transmissibility ratio, and here it is what is called maximum relative displacement of your unspun mass to the spun mass for the given road input amplitude, called the rattle space requirement, and then road holding. So when I say road holding, it's again Z0 minus Z2 max by Z0. So the relative displacement of your unsprung mass to that of the road elevation profile, this ratio, when this is maximum, this ratio to be minimum, to have always the road contact, the tire patch should have a contact with the road. So when you are not driving your vehicle, that is in a static deflection. That's the maximum deflection possible. When you drive your vehicle, about that it is going to vibrate. So when it is vibrating, your contact patch or the contact patch or the tire deflection is the measure of your contact patch. If the tire deflection becomes zero, what will happen? There is the point of detaching from the road surface. That means there is less load that is acting on that particular wheel. When there is a less load acting on that particular wheel, and which is primarily required to cater your traction or lateral forces, and they are going to be less. So that is very less, then poor handling would happen. So to have a good handling and a good traction performance of a vehicle, you should always have a load felt on your axle, and then you get a good hold of your contact patch on the road. And as long as that's there on all four wheels of a passenger car or all wheels of any vehicle, then you have a good handling capability. So if you look at the requirement of these, all would contradict each other, and that is why this become an optimization problem. The suspension design should be such that you should have to have all three of them met. But if I have my suspension design for first objective, I need to have a compromise with the road holding. If I have to go for this, I need to have a compromise with this. But how can I then win this situation? And that's where you see your role of suspension is not no more considered to be passive suspension. Instead of it is going to be an active or semi-active suspension system. We are going to briefly look at them now. So this is that vehicle which you have already seen on the vehicle data purpose, sprung mass, unsprung mass, and its suspension spring rate and tire spring rate. Of course, here the values of damping of a suspension shock absorber value as well as the tire is not explicitly given, but you can always take it, the data will be given. So I'm just going to highlight the variation of your transmissibility function as function of frequency here. To understand what is this vibration isolation. So that's what I was briefed already. I just look at it. It's a parametric study. So you have three parameters. What are those? One is the mass. Another one is the stiffness. Another one is damping. So when I say mass, stiffness, damping, mass are two, sprung mass and unsprung mass. Stiffness are two, Ks and KTR, and dampings also are two. I consider only shock absorber damping. Why? Because comparing the damping value of your tire to that of shock absorber damping value, that's insignificant, we have seen. So in your model, you have these parameters, right? So in these parameters, vehicle's body mass is not going to be changed. I can vary, play with my unsprung mass. That's what we look at the vehicle with steel wheel, alloy wheel, and so on. So when you have an alloy wheel, the mass is reduced. So when its mass is reduced, is it good? Is it good for a good isolation, or like that? You have to look at it. So what would happen if I vary my unsprung mass, holding the rest of the parameters constant? What would happen if I vary my spring rate, holding the rest of the parameter constant? Or what would happen if I vary my damping ratio of the suspension shock absorber, holding the rest of the parameter constant? Is what is the study now focused for three important objective of vibration isolation, rattle space requirement, and road holding. So in this slide is giving you in a compact form for a vibration isolation. And you see here, as I said, you'll divide that into lower frequency range and mid frequency range between these peaks, and then higher frequency range. There are 9 cases that we are going to look at. So first case is for vibration isolation. So vibration isolation to have, what would be its influence due to variation in unsprung mass, variation in spring of the damper, and variation in spring of your shock suspension system, and damping ratio of your shock absorber. That's how I'm going to look at it. So I feel that you got my point. And look at here now, the sprung mass is fixed, quarter car model. So I have this mass, 1/4 of the vehicle mass, and then KTR tire is not changed, so that's fixed. and then KTR by KS value is 8 here. So KTR by KS value is 8 is chosen, it's fixed here. So then my damping also fixed, it's 0.3. So for this given condition of my vehicle, if I play with my unsprung mass changes, so the ratio of unsprung mass to sprung mass is increases refer to what? Increases refer to what? When sprung mass is fixed, if I increase, then my unsprung mass increases. So this type of line in the graph refer to higher mass, and this is of a lower mass of unsprung mass. So I could see here in this range, lower range until mid frequency, mid frequency range, also there is no influence of this mass. But however, you see that beyond midpoint of mid frequency range, you see that this line is what is referring to a low mass. So that means instead of steel wheel, if I have an alloy wheel, that is going to give me good transmissibility, minimum value of transmissibility. So the main objective is to minimize these functions on y-axis. So I have here minimum value. And of course, the penalty of higher frequency range. But the higher frequency range, you see already what is this transmissibility ratio here beyond this. So that's negligible. So that's called a penalty. So I can prefer now lighter mass of my vehicle for a good vibration isolation, right? And here you look at, if I have to think of my spring stiffness, what should I do? So I hold now sprung mass to mass, unsprung mass to sprung mass as constant. I'm not going to vary it. These parameters are fixed. So I vary only my tire, vary only my spring stiffness of my suspension. So as this value increases, what does that refer to? This value is decreases. So softer the spring refer to the higher value here. So this dotted this line is referring to a soft spring. Soft spring you see here at the low frequency range it is higher value. At mid frequency range as well as here it's negligible. So mid frequency range beyond this resonance state you see this softer spring is better isolating. Why do I say that? For any given frequency, if I chose this like that, look at here this value and here this value. So here the value is very less compared to this value because the log scale is 0.2, 0.3, 0.4, so it's more. So this value is preferred. So if I have my spring, soft spring instead of hard spring, which is referred here, that's going to act as a good isolator. So I need a soft spring for my vibration isolation. And that is not much spelt in this higher ranges as there is a very significant deviation. So what is preferred for isolation? A softer suspension spring. When you come to damping, what is preferred? It is not a high damping value. High damping value, of course, needed to account for the nearest part of your natural frequency of your sprung mass. But apart from that, you see the value is not favoring. So the one with this lighter damping, 0.1, that's favor in mid frequency range as well as a higher frequency range as far as transmissibility is concerned. So what is the conclusion here for an isolation? I needed a less weight unsprung mass, maybe an alloy wheel instead of steel wheel, and I should have a softer suspension spring. I should have a low value of damping. If I have that, I would have better isolation. So if you take this point in hand and we look at another requirement, they would contradict. So that's all evident from these plots, right? What are these plots? It's nothing but your magnification factor, what you have studied in force response studies. Similarly, what is that? Your transmissibility ratio. For a single degree freedom you have studied, now it is for 2 degree freedom, that's why you have these two peaks. So if you have n degree of freedom, your curve would be like this. You would have a frequency corresponding to individual degree of freedom its vibration, right? So looking at the requirement of suspension travel that defines your rattle space, that is what is the ratio of relative displacement of Z0, Z2 minus Z1 by Z0. Do I have put the same here while defining? Yeah, Z2 minus Z1 by Z0. And that value to be minimum. So this value to be minimum. So you can, I leave it to you, you can critically go through that. What is preferred? Is that the light weight of unsprung mass is preferred here? If I ask you that question, you look at here the graph. So this is here, it's down, whereas there is a penalty here. If I go for heavy weight in mid frequency range, it's not preferred, but in higher frequency range, it's good. Like that, see this requirement is not easy, it's complex. So similarly, you see here spring rate, what's happening. So I would prefer my this range is more, means that is softer spring, because KTR is fixed. So softer spring refer to 10. So this dotted line. So in the lower frequency range, it is not preferred till here. But beyond the mid frequency range, and here it is again insignificant. So you see this is different now. And again, damping, if you look at the high damping only is preferred. So the low damping is not preferred at all. Is it not? Yeah. So the high damping value is preferred for this. So the requirement of accommodating space between bump and rebound stops, my gadgets or my components of suspension, I require that a compromise in isolation. So stiffer the spring, stiffer the more the damping value, or the mass values, the light mass and stuff, that this mass preferred as completely in opposite requirement, right? So that is what is the suspension travel requirement. When you look at the road holding again is defined by Z0 minus Z2 by the maximum relative displacement between them by Z0. So for example, that's what I was telling, your tire deflection delta, let me say, that's going to be delta Z, let me say in Z direction, that's going to be 3 centimeter. 3 centimeter. When the load is varying during drive condition, this would be fluctuating. So that fluctuation should not take this to 0 value. So when it goes to 0 value, what would happen? There is the loss of contact of road. So this is described by now Z0 minus Z1, Z0 minus Z2. So the relative displacement is what is going to dictate on this top, on the tire deflection. What is maximum possible tire deflection for given Z0 is what is going to be taken as the tire dynamic deflection ratio. So the tire dynamic deflection ratio, smaller the tire dynamic deflection ratio, better the road holding. If it is more than the road holding is the question mark. Again, if you look at here, you see the contradicting requirement. You require a stiffer spring than a soft spring. You require high damping value than low damping. Of course, in the mid frequency you have low damping, but overall you see this frequency range requirement is high damping value, which is again contradicting. So such kind of contradicting requirement cannot just be met by a passive system. Cannot just be made by this passive system. That's what, again, to see here requirement of suspension spring, I just have brought in one case study you can go through. So the optimum control strategies of these three are defined by these parameters, right? 1, 2, 3. So I had to find this RMS acceleration. Today we discussed how can you find out, and RMS value of suspension travel. I understood that's given by Z0 minus Z1 max by Z0, and this is tire dynamic deflection value that's given by Z0 minus Z2 max by Z0. So these are all values to be minimum to meet these design requirement, and that can only be met through a passive or semi-active suspension system. So the passive suspension system is what so far we are discussing. The figure 7.6 can be referred. You have here, these values are fixed here. So if these values are fixed for isolation, the compromise in the holding handling is coming into picture. So I know my requirement according to the operating condition of my vehicle and load of my vehicle variation. Then I can replace this suspension by an actuator, force actuator with the electronic control system and power supply required, measuring the sensors, applying sensor and measuring this motion, vibration. I can have an appropriate control strategies to have whatever I needed according to the excitation that comes. So that's what is an active suspension system. That's most popular. Though it's popular, it is not very popular compared to that of semi-active suspension system. Is because the requirement of power is more here, and it's very complex compared to that of semi-active suspension system. And most importantly, if it malfunction, it won't. If it malfunction, then it will be failure. Whereas that can be taken care in this case, semi-active suspension system, because you have a passive spring here, and that would always support. You have the failure of your control system. This entire thing would become case one of a passive system that can account for the scenario, right? So here the advantage of semi-active suspension system is power requirement is relatively lesser than that of active system, and the complexity is reduced, and so on. So this would always measure this amplitude, whatever the three objectives that we have seen can be optimized for its minimum level through these sensor values and the appropriate control strategies. I will just show you in the upcoming slides. It can be varied, the damping value, the viscosity of damping value, the flow of damper fluid. Viscosity can be varied in no time when advent of fluids called electro-rheological fluid or magneto-rheological fluid by means of applying electric field or a magnetic field. So they are very popular and taking their application advantage in suspension system. And you see here what an active suspension system can do. It can vary the height adjustment, and it can adjust the roll, dive, spot. I leave it to you to read. And then what is this electro-rheological fluid damper is, you can see on this graph passive system, and then when it is introduced, what is happening. So you see this, whatever the amplitude here of accelerations fall down, and it is reduced here. And this basically would be having a concentric cylinders where the magnetic powdered fluid can flow through this concentric cylinders, can be realizing across it's an electric potential, and that would vary the fluid property. According to that variation of viscosity, you would have a varying damping force in your system along with your spring, and that would account the requirement of your all three aspects, right? And another one is magneto-rheological fluid dampers, where the fluid, ferromagnetic fluid suspended in carrier fluid, when it is magnetized, that can change its fluid state to a solid state in no instant, just like that. So you would be able to play around with the magnetic field applied according to the requirement of measured signals from your sprung and unsprung mass. Those control strategies can be achieved through this kind of fluid easily. And those strategies are called on-off control strategies. I just mentioned here two. There are many research articles are available on this control strategies. So on-off control strategy, let's see if this product velocity Z1 dot and Z1 dot minus Z2. So Z1 is sprung mass velocity, and relative velocity of sprung mass with the unsprung mass greater than 0, then the maximum should come. So refer to a firm damping is required. So I require a damping force more. If it is other way, it's less than negative value I get, it is a soft condition. So this kind of strategies are finalized with these researchers based on to meet all three requirements. And another one is called a continuous control strategy given by Alan C. Sankar and Jolene Miller. And they take this product as to have a minimum damping when, or to have a damping by this formula for this situation. And these are the observation for passive and active suspension system when it is employed. The response of your acceleration ratio, right? Semi-active and passive system RMS acceleration ratio, and you would see that the semi-active suspension are best performing than that of a passive system. And road elevation profile is this for this test conducted, right? And this is again for dynamic tire deflection. So this one is for an acceleration ratio, that's for isolation purpose, and this is for handling purpose. On this specific road profile, this tests are conducted. So with that, I stop this lecture, and I hope that you have got excited to know more about studying suspension, not only now for ride aspects, also for road holding, handling aspects that we will see in our lateral dynamics time. Once again, looking at the suspension for its stability and its rollover stability and so on, right? Okay, good day to all. I finished by this second lecture, the module 2, which is ride dynamics part of our lecture. If you have any doubts, you can ask. Otherwise, I'll end the lecture. Do you have any doubt? If not so, I'll stop lecture now.